Hi there! In this video, we're going to be learning about hypothesis testing using the binomial distribution. To begin with though, we'll just learn about what a hypothesis test is. And I know there's a lot of notation here, but I'll try my best to break it down for you. So in essence, a hypothesis test tests a known statement about a population parameter against a new statement. It tells us whether we can accept or reject the original statement. So, for example, a known statement could be that 60% of students pass a test. And then this new statement could be the amount of students who pass has decreased. And that new statement is normally influenced by some evidence that's come into fruition. For example, one year, maybe the cohort scored very low, and that made them reassess this known statement that normally 60% of students pass a test. Obviously, it's not going to be 60% every year, or every time the test is taken, but what this test does is it tests whether a value is so unlikely to happen that this new statement is correct. For example, let's say no students pass the test. Then it makes sense to think that something's changed, because 60% to 0% is a huge decrease. So then we would be able to reject the original statement. But if it's something very, very normal, like 59%, something that is just because probabilities aren't constant and cohorts change and it's different students. If it was 59%, you wouldn't really bat an eye. But usually we'll be looking at somewhere in between. So on the edge of what's considered likely or unlikely, or when we would accept the original statement or reject the original statement. Okay, so here are the steps of a hypothesis test. First of all, we define the population parameter P in context. P is just the probability of success. So if you think about the binomial distribution, that is what we normally see when a trial is successful. The probability of that is going to be P. And then you state the null hypothesis, which is your known statement. And then you state your alternative hypothesis, which is your new statement. And your null hypothesis is denoted by H0, whereas your alternative hypothesis is denoted by H1. And then you define a test statistic, which is the number of successes, and it's denoted by X. And this is kind of linked to the probability, because this is the probability of success, and this is the number of successes. And this is normally our random variable that we use. And then after that, we write down the sampling distribution of X under H0, which in this case, it'll be the binomial distribution. After that, we state the significance level, or alpha. This determines how unlikely the value needs to be before H0 is rejected. In other words, if it's something like 5%, then it has to be less than 5%. The probability of this occurring has to be less than 5% for us to reject our null hypothesis. And then once we've defined all of this, we can actually calculate either we can calculate a test for significance or the critical region. And the critical region is the set of all values of X that would cause H0 to be rejected. A test for significance just tells us if we can accept or reject the statement. And then at the end, you have to write a conclusion. And this is a lot of stuff, and you might not understand how to do any of this, and that's fine, because we're going to do an example which will hopefully clear things up. So usually you will get wordy examples, or examples in context at least. So yeah, let's see what we can take away from this. So in a past census of employees, 20% were in favor of a change to working hours. Okay. After making changes to staff contracts, the manager now believes that the proportion of staff wanting a change has decreased. The manager carries out a random sample of 30 employees, and 2 are in favor of a change in hours. Test the manager's claim at the 5% level of significance. So, let's think about what we're given here. Or in fact, let's look at it in terms of this set of rules, or set of steps. So all I've done here is I've underlined the important bits. So the first step is to define the population parameter P. So a population parameter, well, that is just the probability of success. So we're just going to say P is the probability that an employee is in favor of a change to working hours. So all we're doing is defining what P represents. We're not actually stating what P is, because that's what's up to debate. So now we can move on to the next step. State the null hypothesis H0. So H0 is this, because this is the original statement. In the past census, 20% were in favor. So what we can say is, all you have to do is put H0 to determine that it's the null hypothesis, colon, and that P equals 0.2. So we're saying our original statement is that the probability that an employee is in favor of a change to working hours is 0.2. So that's all we're saying. And now we want to give our alternative hypothesis, which is H1. If you look back here, next is finding an alternative hypothesis. So now what we do is we look and we say, wait, this is our H1. The change has, the proportion of staff wanting a change has decreased. So we can say that P will be less than 0.2, because we know that this alternative hypothesis is suggesting that it's decreased, so the probability will be less. Okay, next we define the test statistic X. So our test statistic, again, like P, we're not actually going to give it a value. Just like if you were defining it for a random variable, we'll define it now. So we'll say that X is the number of employees in favor of a change to working hours. So usually P is the probability that this occurs, and then X is the number of occurrences, as you can see. Okay, and then we write down the sampling distribution of X under H0. So this sampling distribution is X, is the binomial distribution. So we write X is binomially distributed our n is this, 30 employees, because it's a random sample of 30. And our probability, it's under H0. So we use whatever probability is in H0. So that would be 0.2. So you can see up till now, or in fact, we also have to state the significance level, alpha. So we can say that alpha equals, well, this is the level of significance, 5%. So we can say 5%, or, sorry, it would be 0.05, or put it in decimal form. Okay, so up till now, you can see that we haven't really done any calculations. All of these steps have just been defining these different terms. And actually, you will get quite a few marks just by putting all of these out and knowing what steps you have to take. And it's only when we get to step 7 when we actually calculate something. Now, either we're testing for significance or we're finding the critical region. Well, here it says we need to test the manager's claim. So we're going to test for significance. So how do we do that? Well, we see that 2 are in favor of a change in hours. So how do we actually test for significance? Well, we know that there are 2 actually in favor for a change in hours. And this is the evidence we use. What we do is we find the probability that the test statistic will be less than or equal to that value. So we're going to test what we're going to find the probability of there being 2 employees, 1 employee, or 0 employees in favor. Okay, and when we do that, we find that it's 0.0442, like so. But now you can see that that is less than our test statistic. So our conclusion, which is our last step, if I go here, our conclusion is that there is not enough evidence, and this is the wording you should probably learn. You either say there is evidence or there is not enough evidence. And sorry, I meant there is evidence in this case to show at the 5% level that the proportion of staff wanting a change has decreased. Hence, there is enough evidence to reject H0. And this is the way you always should put your conclusions. So we say there is evidence to show, or there is not evidence to show, and then you say what the significance level is, and then we say that the proportion, you just relate it to the context, whatever it's asking, and we say there is enough evidence to show that it's decreased or increased, or there isn't. And then you say, hence, there is or is not enough evidence to reject H0. So now we've rejected H0 because we said the probability of this is so low that it's lower than the significance level, so we can take this to be our new null hypothesis. And this here, the reason why we say x is less than or equal to 2 rather than x equals 2 is because every single value of x below 2 will be even more unlikely than 2. So that's why we also include those. And it's always a cumulative distribution. So yeah, and we actually can take a lot of information about it out of this question. For example, this is our n. This is what we use to test against. So this is our x, if you're thinking in terms of that. And this is our alpha. So there's a lot of stuff that you can take from the question. Alright, so let's just now go back and relate all of this to the binomial distribution. So our population parameter and our test statistic are quite self-explanatory, but our null hypothesis will always be in this form. P equals some probability A. And then our alternative hypothesis has three forms. Either the probability there's evidence to show that the probability decreases, there's evidence to show the probability increases, or there's evidence to show that the probability has changed, but we don't know which way. And these two are called one-tailed tests. Oops. And this is called a two-tailed test. So what we just did there was this one. So it's a one-tailed test. And the sampling distribution for binomials will always be in this form. The significance level, again, is all you need to remember that it's in a decimal, not a percentage. And then, yeah, everything else is kind of the same. Okay, so now that we've done that, we can move on and look at how we can find a critical region, which, if you remember, for 7, you either test for significance or find the critical region. And it's all the same. So every other step is the same up to 7, and then it changes. So that's the only difference, really. Now, before we move on to this, I'm actually going to prove that, and I'm just going to show you how we do 7. So now we're trying to find the critical region. So what we need to do is we need to find the set of all values that would cause H0 to be rejected. So that's all the values less than or equal to 0.05. Okay? And we want to find the set of all values which this would be true. Or that all those probabilities would be true. So, okay, let's work through it then. So we know that probability of x is less than or equal to 2. We know that that is less than or equal to 0.05. Let's try the probability of x is less than or equal to 3, because this will have a higher probability than 2. So if you put that into your calculator, you will get 0.1227, which is, this should be an equals sign, and that will give us, that will be actually greater than 0.05. Hence, we have found our critical region. Our critical region, or our CR, is x is less than or equal to 2. Because there is a significance, because x less than or equal to 2, is less than or equal to 0.05. So every single value less than 2 will also have as low probability. So x is less than or equal to 1 will be a lower probability than that, which is fine because it's still lower than 0.05. It's x is less than or equal to 3 that actually changes things. So that makes our critical region x is less than or equal to 2. And since our value here is less than or equal to 2, it lies in the critical region, so that's how we can get to our conclusion from there. If you have a lot more values, you can also use, on your calculator, you can use the list option, which gives you all the values for different x's here, or lowercase x's. Okay, so that's the process we take on a one-tailed test. On a two-tailed test, it's actually quite different. So let's do the same thing. Let's just answer this question going through the steps. And this is a two-tailed test now. Okay, so it says that records show that the proportions of trees in the wood that suffer from a particular disease is 15%. Chloe thinks that the recent weather conditions may have affected this proportion. She examines 20 trees. Using a 10% significance level, find the critical region for a hypothesis test of Chloe's theory. So that's part A. So let's do that. So what we're doing is we're just going to go through the different steps. So let's start by defining the probability parameter. So the probability parameter is the probability that a tree has a particular disease. And then next, we want to define the null hypothesis, which we can see that that's 15%, so the probability is 0.15. And then the alternative hypothesis, in fact, I'll save room. Well, now you can see that it hasn't actually told us whether Chloe thinks it's increased or decreased. She just thinks it's been affected. So now it's a two-tailed test, because we don't know whether it's going up or down. We just know that we don't think it's 0.15. Okay. And then next, what we do is we define our test statistic. So x is the number of trees with a particular disease. And then we can move on and define our distribution. So it'll be a binomial. Our number is 20 since she examines 20 trees. And we use the probability from H0 as our P. And then I think we've got everything there. Yeah. Just the significance level. So alpha equals this, which is 0.1. And now for step 7, we want to find the critical region. So it's kind of like what we did here. So we want it to be less than the significance level, but because it's a two-tailed test, we actually have to half the significance level on each side. So we need to look at both sides to find the significance level. So if we look at the lower side, let's start at the probability x is less than or equal to 0. So we get 0.0388, which is less than 0.05. Remember, we have to half the significance level because it's a two-tailed test. And then we bring it up by 1 and see if anything changes. There we go. We get one that's greater than 0.05. So we know that the critical region so far is x is less than 0. Or in other terms, we could just say x is equal to 0 because there's nothing less than, you can't have negative trees, so you won't get anything less than 0. Okay, so that is the bottom half, or what we call it is the lower tail. And here we have the upper tail. So let's look at the other side. So the highest number we can have is 20. But what's going to happen, and if you put this into your calculator, it's going to be really small. And it's not until you get to, so you can continue, for example, you can go from 20 and find out what that is. And then you can just keep going. But when you get to this point, where you get to x is greater than or equal to 6. Sorry, greater than or equal to 7. Remember to put into our calculator, we need to modify it a little bit. But that will give us 0.0219, which is less than 0.05. And then when we move on to 6, we actually get a value that is greater than 0.05. So now we found our critical region there as well, because we reject H0 when it's greater than or equal to 7. So our critical region, in fact, I'll rewrite this, is when we have x equals 0 or x is greater than or equal to 7. So when we have a one-tailed test, we only worry about the one value, the one side. In this case, it was the lower tail. So that's why we keep the significance level the way it is. But when we have a two-tailed test, we need to divide the significance level by 2. Okay? And then it asks to find the actual significance level on the test based on A. So the significance level of the test will be the probability that x is equal to 0 plus the probability that x is greater than or equal to 7. Because we're taking both of these extremes, and then we get 0.0607 or 6.07%. Sorry, I forgot to put part of the question in, and this is gonna pop out a little bit, but it now says that Chloe finds 8 trees that have the disease, and now we need to comment on this finding in relation to part A in Chloe's theory. So if you have 8 trees, and we know the critical region is x equals 0 or x is greater than or equal to 7, well, 8 lies in that region, and so we can say that because it's in the set where H0 is rejected, we can say whoops, let me change color. There is evidence at the 10% significance level to reject 0 and to show that, or we want to link it to Chloe's theory and to support Chloe's theory that the proportion of trees affected has changed. So yeah, they're always lengthy conclusions, but you have to do them. And yeah, so that's how you'd find the critical region of a two-tailed test. And even if you're testing for significance, which is the other thing we do on step 7, you still have to halve the significance level. So, in fact, let's try and do that again. So let's say there's a D that says test for significance. Now, again, we've already figured it out, but what we can do is let's do D to show that. Now, the thing is, you might be wondering which way to go. And what you need to do is you need to get MP for that. So you need to find the expected value, which is 20 times 0.15. So 20 times 0.15 is 3. Now what we want to try and say is do the amount of trees that have been observed, is that higher or lower than the expected value? And since it's higher, because 8 is greater than 3, what we do is we look at the upper tail. So we say, what's the probability of x being greater than or equal to 8? Or 1 minus probability of x is less than or equal to 7, and that will be less than 0.05, which will also prove it. So you do also halve the significance. All you need to remember is you need to use the expected value to see which tail to take. Thanks for listening.